Okay, here we go. We have a completely do-it-yourself frequency counter or frequency generator. It's got a frequency counter on the front, and you can change the different ranges from like I don't know, less than 100 hertz up to like 200 kilohertz or more. I think it's supposed to go up to a megahertz actually. And we can independently adjust the frequency here. Bring the frequency up. 14 kilohertz. And the voltage puts out a nice square wave. Okay, so there's 2 kilohertz. Okay, here's one thing I like to do with have the FETs, and the problem is that they tend to burn out, and this is, you know, I probably want to wire stuff up, but if you keep on unsoldering circuit boards and resoldering them, the pads will lift. So I like to use, well, this is a 14 pin dip connector, and I took my pair of dikes and carefully chopped it in half, and then I chopped one of these sections in half to get a 3-pin, and those pins are just the right size to fit onto the transistor, so you can plug in and unplug, you know, let's see if I can get that on there, transistors into that type of thing. And I think I might add a little capacitor to this circuit to, you know, you can store up a little charge, pull these things off, and then you get a big burst of, you know, capacitors can give you a big burst of current when the thing switches on, so you can get a higher peak current. So I'll look around here and see if I can find some capacitors to build into this circuit. And let me take this circuit board out and we'll start building it. Okay, anyway, so I have this 3-pin connector and this circuit here, and might try to get a capacitor because that will give you a higher peak current, and be able to use this as a little plug to plug and unplug transistors if I burn them out. So it looks like this thing is coming together, and then we'll integrate it onto this thing over here, and we'll have a pretty cool power supply to do some interesting testing. Okay, maybe I won't put the capacitor in there. We'll just try it without it first. So here's the diagram of the FET. Well, first of all, let's look at the FET I'm going to use. I'm using a IRL 640A, and it's capable of holding off 200 volts, 0.18 ohms, 18 amps turn on. And here we go, from this side to that side, it's gate, drain, source. So gate is where you put the signal in, drain is positive, and source is negative. And so here's some FET circuits. Gate is where you put your signal in to be amplified. Voltage plus goes into the drain, and voltage minus or ground goes out the source. Okay. And so I'm going to try to wire this up so we can be true to that circuit. And this is our little 3-pin connector, and here's our FET. Remember, it's here. Let's see if we can see this. Gate, drain, source. Okay. It's hard to see that gate, drain, source. Okay. Okay, so I soldered that 3-pin socket on there, and I started soldering these. Well, they use a little bit heavier duty wire, and this is something that I had around here. It's 18 gauge, and I just soldering those one to each pin on that socket. Have one more to solder. Okay. Since these are just dots, I'm bending the wire over to solder onto the adjacent contact So I'm bridging the gap with the actual wires. And I'm going to probably check this in a little bit to make sure that there's none of these are shorted together. Okay, there we go. And oh, again, there's the front of it. We're going to put the transistor. Okay, there's the transistor. Okay, I'm just doing some testing with an inductive load, and the signal out is not looking the greatest. So maybe I need the, I think on my other one I had a FET driver driving the FET. So maybe I need to put a FET driver on this one as well. So let me see, I might have to get another socket on this thing. Okay. Okay, I guess it looks like I put it at a lower frequency. We're about 200 hertz now. And it looks like there is, let's see if we can, is that shut off maybe? There's a lot of ringing there. So maybe I need to put some damping somewhere in the circuit. I might try damping, maybe the input. Maybe that will get rid of that. Maybe that will, maybe I won't have to put a FET driver on it. We'll see. Okay, so I just put a resistive load on there instead, and it looks like that kind of fixed a lot of the problems here. Let's see. Okay, so we got a much better waveform there. Come on. Okay, let's. Okay, so let's see. We're at what, 2 kilohertz right now, and we'll let's see. Where's our potentiometer? We'll crank that up to, look at that. So this is 8 kilohertz, and the waveform's starting to become not as nice anymore. And I think I want to go up to higher frequencies than that, actually. Let's see, we're 5. Okay, so it kind of stops oscillating at a certain point. But 11. Now I think this signal generator, let's take a look over here, has jumpers, and those set the frequency ranges. So maybe I'll go up to the next frequency range and see how it behaves up there. But it looks like the waveform's already starting to get a little bit distorted at about 11 kilohertz. And I think I wanted to go up higher frequency than that. So we may have to put a FET driver on this guy, and that may fix the problem. And of course, inductive loads could be a problem as well. Okay. Should be interesting though. Okay, I just wanted to test one more thing at the amplitude. Because remember, this should be amplitude dependent. When I bring the voltage up and down, it should be changing the amplitude of our waveform. And here, let me get a better view of this thing. Okay, there. So I'm twiddling the dial here up and down in voltage, and it's changing the amplitude. So we're definitely going to be able to make a variable high power signal generator. I just may need to do some fancier input into the FET to make sure I get the bandwidth, because I really want to go up faster than this frequency. In fact, I'd like to go up to make it a very broad bandwidth device, so we can do a lot of different experiments with it. Okay, but definitely we can crank up the voltage, and this power supply goes up to 24 volts, but the same idea can be applied to even bigger voltages. Okay, so it looks like we're doing pretty good so far. Okay, so it looks like this is what I used on my previous driver circuit. It's TC4424AV, and it is a FET driver. And what that does is it has basically an N and a P FET, and it switches the current in and out of the FET very quickly. It basically dumps a lot of current into the gate, and then it will switch it back down to 0 and dumps all the current back out very quickly, because you need to do that to switch it off quickly. And well, here's kind of the diagram where pins 3 on this side over here and pin 6 over there are the ground and the power to it, and it's a dual FET driver, so there's an in on this side and an in on that side, an in A, in B, and out A and out B, not. I guess it's an inverter one, but that's okay. I believe that's what it means. The overline, I believe it's inverter. Okay, and so I guess we will put in a socket onto our circuit here. I'm trying to follow the floor. And we will try to implement a FET driver and see if we can improve the bandwidth of this circuit here, this little chip. Okay. Okay, so I just got through soldering on this socket, 8-pin socket for our little FET driver here. And the circuit's going to call for a capacitor, so you can have instant power right near the circuit, because it's going to switch this thing very fast if you want high bandwidth. And let's see, this capacitor, I think this is the same capacitor I use in my other circuit, 200 microfarads, and it goes up to 50 volts. So we're going to have to pipe over the constant 6-volt power supply over here into this FET driver, because you don't want to put too high a voltage on it. The other variable voltage that we're running to the FET is for the output, and so you don't want to put high voltage on the FET driver itself. So we'll need to have 2 power supplies on this board as well. Of course, they're sharing the common ground. I have the common ground tied together on this one, so that'll just be an extra wire coming over to this guy. Okay. Okay, so here I have mounted the capacitor onto the circuit, and it fits nicely right under here. And again, the ground is on pin 3, and the positive side, you know, electrolyte capacitors have a plus and a minus side, and the plus side's got like a little crimped end, and it usually has some plus signs that tell you it's plus or something. It'll indicate somehow. You don't want to charge these backwards because it will destroy the capacitor. And so we're going to have to supply a constant voltage. According to the spreadsheet here on this device, it can take 4.5 to 18 volts, but I don't think that the FET, let's look back at the FET, the FET wants to have a gate voltage that's probably not that high, and our power supply is going to go up to 24 volts anyway. Let's see. Low input gate capacitance. Gate threshold voltage is 5 volts. Okay. Yeah, I don't think the gate probably wants to go that high though. So we do need at least 5 volts to turn it on though. So we're going to be operating at 6, so hopefully that's high enough. Source drain. Okay, I'll have to look for it, but I suspect it's not going to want to go up to 24 volts, and the other one can't go up to 24 volts anyway. So that's going to be a limit. So we'll try to keep it with the 6-volt constant power supply we have on this device here. Okay, I just soldered the capacitor on for the power of this FET driver, and I'm going to start wiring the necessary things to power this thing. And of course we have a common ground, and the common ground is going to the source here. Remember, it's gate, drain, source, and so we can pipe this. I'll get a little wire to run from here to the ground of this capacitor, and we can pipe the ground side over to to this side of the capacitor, and of course we're going to have to get the positive from the other side of the constant power supply on the main from the main power supply over here. So we'll have to run a second wire to get power to this side to power the FET driver. So this FET driver will be powered at 6 volts, and this one will be powered at a variable voltage, so you can have a variable output. Okay, and then after that I'll worry about wiring the inputs and outputs to the FET driver and the FET, so we can get that all up and running. Okay, so now I have the wire here going from the source to the ground of our FET driver, and I soldered that on the back just by using solder blobs, because the only board I could find here was these annoying ones with the little patches. So I'm just connecting the wires underneath and solder blobbing it together, but not my first choice. But you know, we're living in hard times now with the totalitarian communist takeover of the world by the evil New World Order. So, gotta do what you can, right? Okay. So the next thing I'll do is just run a wire out so I can connect it to this power supply for the positive side, and we'll get the power taken care of. Remember, that's the first thing you should worry about is power, and then if you don't have power, nothing's going to work, right? Okay, and then we'll worry about wiring the outputs to the FETs. Okay. Okay, now I've soldered on this wire here to the positive side, and I've connected it to the capacitor lead underneath. Okay, and so the next thing we're going to do is I guess we'll put another wire just for the input of the FET, because now the signal is going to come from our signal generator into the FET driver, and then out of the FET driver to the FET. Okay, which I've removed them while I'm working on the circuit. Okay, and so we'll just add an input wire. We'll just use the top. So this is a dual FET driver, and I'll just use the top pin number 2. So this one is not used, and so pin 2 will be right there. So I'll add an input there. The output will come out on that side, and we'll route that into the gate. Okay, and then I think our circuit will be done. Okay. Okay, so I have the FET wire input soldered on. It's not super pretty, but I checked it with my volt ohm meter over here, and it will be functional. The circuit seems to be good. And so now we're going to change the gate. Now remember, we're doing high-speed stuff. You want to keep the wires as short as possible to decrease stray inductance or parasitic capacitance. And so I'm going to probably cut the gate, remember, is this far pin over here, and I'm going to have to wire it out of our FET driver, because this pin number, let's see, what's that, 1, 2, 3, 4, 5, 6, 7, so it's pin 7 is going to come out over here, and it's going to go into the gate. And so I'm going to go on to keep that wire short, so I'm going to have to cut this wire and make it a little bit shorter so we can power the FET with that. Okay. And so I think I'll do that right now. Cut this wire shorter, strip it back, and solder it into place here. And try to keep this wire as short as possible, but still a reasonable length. You know, when it gets too short, it gets hard to work with. So, I mean, we're not going to that higher frequencies. So, just in the tens of kilohertz, maybe the hundreds of kilohertz. But still, you're still going to need a FET driver, I think, to do that. Okay. Okay, so now I've rewired the gate to go into the FET driver output on pin number 7. And again, using the solder blob method on the back to hook these pads together, because they're all separate paths. And I'll just test out the whole circuit before I put power onto it, because you always want to double and triple check. Because once you put power on it, it's too late. You'll destroy stuff. Okay. And let's see. So we got the power lead here. We got input to the FET. I might just hook up the FET driver to the circuit and power it up and make sure that we're getting a good output out of the FET driver. And then if that looks good, then we might power up the add the FET to the circuit and make sure we're getting good output there and see what kind of bandwidth we can get. Okay, remember to test your circuit out. Make sure that all the continuity is correct and there's no shorts or anything. Okay. And I've tested all the contacts, all the power from there to here, and everything looks good. I'll try putting the chip in and see what happens. Okay, so I'm going to put I just turned the power on to my signal generator, and this is the input to where the gate's going to be, and it looks like we're getting a good square signal there. Let me adjust this a little bit. Okay, so a good square signal, 6.2 volts peak to peak, just as we expect, and I think we're good to go. So we can try to put the FET in and see if we get power out of it and see what that looks like. Okay, it looks like I was trying to use this clippy thing for the probe of the scope, and it looks like it's not getting any signal through it, so this cheap Chinese crappy thing, I guess, broke. Let's take a look here. So here's here's our signal, and it's the output of the FET, and I can see we got 3.3 volts. That's what that is. I'll twiddle this up a little bit. 7, so we're getting variable output, 16 volts, 17, 18. So it looks like, of course, we're clipping there. Let's see, I'll have to figure out how to shift that down, but definitely variable output there. Okay, as we twiddle the knob here. So it looks like our power supply is working, and I'll have to test the bandwidth. See what kind of, it looks like a good square wave coming out. Of course, this is only, what, 900 hertz right now. So let me see, I'll have to twiddle up the frequency and see what we can go up to. Okay, there's 7 kilohertz, and the signal's looking pretty good still. See, 7 kilohertz. I might have to go up to the next scale and see how fast we can go, because I'd like to go up to higher frequencies. Well, it looks like our circuit's working pretty well, though. To change the frequency bands, they have these jumpers here, and it's set on the middle jumper right now. I'm going to move the jumper up 1 to the next frequency band up. Okay, and that should be a factor of 10 higher, so we will see how that works. And I turn the frequency down on our potentiometer, so I'm not going to be screaming fast, because I don't want to mess up the circuit here. Okay, so we're about 3.9 kilohertz, and we're getting a good signal out of this guy so far. Let me just put this up here. This light's annoying me. Okay. And, oh, what happened to our signal? Oh, our probe came off. Okay, so there's our signal, and we'll try twiddling up the frequency. See what we can. Okay, so it looks like, oh, it's starting to get a little bit sawtooth, and that's about 26, but we're still getting a power out of it. Okay, the signal is starting to drop around 40 or 50, so that's going to be probably our bandwidth, although I would like to push that up a little bit. So so 21 kilohertz, At 26, here's 26 kilohertz. And, okay, so definitely our response is dropping right around there. 40, 50 kilohertz. Okay, so we're going to have issues getting power above that, so I'm going to have to see, maybe we need a higher voltage on the FET driver or something. I'm not sure. I don't want to add another power supply if I don't have to, though. So we'll fiddle around with that. Maybe this will be good enough for now for initial testing. I don't know, I've built some power supplies that have over a megahertz bandwidth. Maybe I need some damping resistors in there or something, but it doesn't seem like it's ringing too much. It just seems like it's just having issues turning on. Maybe I can change the duty cycle a little bit, but that will skew it at the low frequencies then. I'm going to fiddle with this see if I can adjust some knobs and make this response a little bit better. Okay, again, here I've moved the jumper up to the high scale, and we're at 60. Let's just bring the frequency up. It's 90, 100 kilohertz. We're still seeing output, and again, could be due to the impedance of the load. But we're definitely at what, 100, over 100 kilohertz. So it looks like the oscillator's becoming a little bit unstable up there. So that's that Chinese circuit, maybe. It's not really being super stable at this frequency. Okay, 150 kilohertz, 170. Of course, our signal's starting to drop some, but maybe if we had a lower impedance load. I think I'm pretty happy with this circuit. 233 kilohertz, and so I think things are looking pretty good here. So maybe I will put that together, maybe add a capacitor to that, but definitely pretty good signal. Definitely good for my experiments I'm planning. Okay. So anyway, this is Dr. Janes, and thanks for watching. Okay, so I'm doing some testing now with an inductive coil, and I'm getting huge back EMF spikes that are coming back through the scope, and it's actually, when I turn up the power, it's somehow feeding back into the oscillator and causing the oscillator to become unstable, which is going to be a problem. So I really wanted to use this to power inductive loads, and so I'm going to have to figure out a way to, I guess, protect the oscillator from these spikes that are coming back. It's really annoying. Okay, so I'm having some issue now. I'm trying to drive coils. I'm trying to drive it to too high of a power. What's happening is that it's starting to self-oscillate once I go above a certain threshold, and it's been getting worse. And I think I might have figured out what the problem is. I think because when I drive a resistive load, it doesn't have that problem. I tried clamping the coil with a diode to stop the back EMF and check the FETs. Everything seems to be working fine. I think what's going on is as I turn up the power to the output, the voltage on the oscillator starts to droop. And when it droops too much, this oscillator is not happy. It doesn't behave properly anymore. It starts to just put out static. And so the only other thing that's being driven off of that is the FET driver. So the FET driver must be drawing more power as I turn up the voltage on the FET, which I guess makes sense. And it's not able to supply enough current, so the voltage is drooping. So maybe I need to put another beefier power supply for the second power supply in the back, the constant power supply. Okay. Maybe that's the problem. Okay, I tried adjusting the load. I had a suspicion that maybe I put a variable resistor on there. Maybe it's just because the charge is not draining off quick enough, and sure enough, as I change the impedance of the load, if the impedance gets too high, the bandwidth goes down because it's just not able to drain the charge off the FET. But I'm going to be driving a very low impedance load, hopefully. A coil, driver coils, that type of thing, transformers, primary. And so it looks like as I decrease the impedance up to the point I don't want to short it out, but definitely becomes more square wave. And so let's go up higher in frequency. We're at 16 kilohertz. And look at that, we're getting a frequency. Let me expand the scale here. Getting a pretty good signal up to 71 kilohertz. So I think we might be golden. I might want to add a I talked about adding a capacitor onto this thing. That's going to definitely give you a higher peak current in your pulse if you have a capacitor there, rather than trying to draw current through all this induction. You know, if you closer you have a current source to your switch, and you might want to try to get the inductance down on the output too, but still 70 some kilohertz is not too bad. Oh, 80 kilohertz. I might try to bump it up to the next scale and see if we can see what the limit of this circuit is. Okay, here we have a 1/4 watt 10 ohm resistor, and I have it hooked up to our oscilloscope, which is going to die soon because I don't think I'm able to charge it anymore. And let's just test that out. And it turns out that looks like it goes unstable also, and it's starting to smoke the resistor as well. So just around 10 volts or so. So maybe it can't drive too low of an impedance without something going unstable. Okay, so I have this step-up transformer, and then I can just power it with my FET here. Power it with my FET circuit over here, and here's my piezoelectric speaker, and we'll just plug this thing in and we'll see how this works. So we can just run this with a single FET. Come on. Okay. And here we go. Okay, that's pretty loud. I'm only running it at 3 volts right now. It seems to be working pretty good. Okay, so there we go. So there you can power the piezoelectric devices with just a single FET and a transformer. Okay. Turn that off, that's annoying. Okay, I finally got my 10-turn potentiometers in, and I get much better control over the frequency. Okay, that's much nicer. See, I can finally tune in the frequencies, even at the upper range. Okay, so I think maybe I will just solder that into the circuit, yeah. Of course, when you go too high, it stops oscillating on the highest level. Okay, reset it and get it going again. Okay, so I just got this thing soldered on there, and we'll test it out to make sure it's working okay. And it looks like it's working good. So I just need to find a way to fasten that. Originally I was thinking about zip tying it. I guess I could still do that, or I could hot glue it down. Not sure. I just don't want it to interfere with the jumpers. That's the only thing. I have some jumpers over here that I have to change, and I don't want the zip tie. The zip tie would have to go all the way around like this. let me fiddle with it and see if I can find a good way to fasten that down. Looks like we're pretty much good to go. Okay. Okay, I think I found some really long zip ties here. So let's see if we can zip tie this this guy right here onto our signal generator without blocking our jumpers that change the frequency. And I think we might be all set then. Okay. Let's see. Come on. I got anything here? Oh, here's something. Again, you can take one zip tie, make sure it's oriented the same way, and stick it through another zip tie to make a big loop. I'm going to try to loop this down between the edge here and the cord, so that will hold the zip tie in place there so it can't come out. And I guess it might have been better if I would have looped it through all the zip ties in the bottom as well. So maybe I'll use this one to do that. I'll loop them through these zip ties in the bottom. It'll hold it in place there. Bring it up between these guys here. Okay. And just over the top like so. And do the same on this one. There's a lip over here I can zip tie it under. And we'll bring it into a full loop here. And oh, come on. Skew it a little bit here. Okay. Oh. You want to get that tight enough that it's going to hold this thing down, hopefully. I don't know. The other option was to hot glue it, so that might still be an option. I guess that will hold it in place. Okay. Zip ties are easier to remove, I think, than hot glue if you got to work on it. Okay. Let me test that out. Okay, so I think I'll start soldering the wires into this because I think it's working pretty good. Maybe it won't serve all my applications, but it's a pretty nice moderate power signal generator. And I'll put the circuit board right on the back there behind the knob. It should be nice and portable. Okay. And I'll just continue to solder these wires on here so I don't remove these clip leads. And we'll see how it turns out. Okay, let's see. We'll always want to test after we get through soldering some stuff up. And it looks like our signal generator is still working. I'm not sure what that is. It's not triggering properly, or it's having some issues. I don't know. It was running it into a short for a little while, so maybe that damaged the FET. Might have to replace the FET. Okay. So maybe I'll zip tie this circuit onto the back here. And then I guess the last step would be the wait. I ordered some 10-turn potentiometers to replace this one, so we can have better frequency control. And maybe I did get some capacitors. Maybe I'll try putting some big capacitors on the oscillator to make sure that it's stable. Because probably if the voltage source is fluctuating, it will cause the frequency to become unstable. Okay. So we'll try to finish this thing up, and it should be an interesting power supply. Okay, so I rotated the circuit up so I can work on it, and I got my small zip ties, so maybe I'll start stringing this thing up. The zip ties seem to be pretty nice about holding these circuits on. So we'll string this guy through and then back down through the other hole. And I'll loop zip ties around the whole thing. Do it on both sides. Got some holes over here. So I get another zip tie into this hole over here. And we'll finish up the circuit. Okay, we got the circuit on, and I got the second set of zip ties on, and I think it's going to take a third set to go all the way around. So we'll get these looped through, move the loop in the right way, and we'll just loop them through the top ones here to complete the loop. Oh, let me get that one out all the way. Okay, and I'll just tighten them up once I get them on, and we should have this back circuit fastened onto the back. Okay, and I got the circuit looped onto the back. Maybe I'll just tighten these things up. So. Make sure we can see the numbers on the front, and I think we'll be good to go. There, get these all good and snugged up. Maybe I'll clip these extra things off, and we'll test her out to make sure it's still working. Okay. Okay. Of course, a pair of dikes works pretty good at clipping these zip ties. Okay. There we go. Okay, there we go. We got it on, and it looks like our signal generator is still working good. We're still getting good signal out of it. Okay. It's looking pretty nice too. Like almost like something from Back to the Future, huh? Okay, here we go. We have a completely do-it-yourself frequency counter, or frequency generator. It's got a frequency counter on the front, and you can change the different ranges from like, I don't know, less than 100 hertz up to like 200 kilohertz or more. I think it's supposed to go up to a megahertz actually. And we can independently adjust the frequency here. Bring the frequency up. 14 kilohertz. And the voltage puts out a nice square wave. And I think our unit is complete. Okay. Nice portable unit. Just plugs into the wall. Oh. Looks like our FET fell out in the back. I like to make things that are easy to maintain. So here we can just replace the high power FET on the output if we want. And there's the FET driver in a socket, so you can replace that as well. Okay. Very nice power supply for doing experiments. Let's plug back in. Okay. Can go through all the different frequency ranges from hertz to almost up to a megahertz. and put out fairly high power at 3 to 3 point something, I guess it's 3.4 to 24 volts at the upper end, and it's a few watt power supply. I think it puts out a few amps, and so actually it's more than a few watts then. Okay, so very interesting. Anyway, this is Dr. James, and thanks for watching.